so I can post it. Anybody got any specific question before I go into some practice problems? No? Cool. All right. So first thing that I wanted to talk about, and we actually sort of just went over a little bit, but in terms of preparation of amines, we have 3 ways in which we can create an amine that's both a primary amine and a terminal amine, right? I mean, terminal meaning it's at that last carbon sticking out on the end there. So see if you can't give me our 3 ways.
أنا حروح يلا وان.
What's up? What's up, Theo? You have a question? No? Oh, okay. All right, so yeah, first step is give me those 3 ways of creating a primary amine that we learned about. Actually, I guess there's a 4th that we know too. Two of these, and so sort of as you're going, I'll give little hints before giving the answer here. So 2 of these are going to start with an alkyl halide. The other one would be if we started with a ketone, and then we also know how to go if we start from a carboxylic acid derivative. Actually, I have one more that we already knew that also starts with an alkyl halide. All right, so I'm going to give you guys a few minutes to complete that, and then I'll go in and give you the answers. Okay, so for the 2 that we just learned about in this chapter, The first one would be the sodium azide synthesis, where you first treat it with sodium azide. That replaces your halogen on your alkyl halide with that azide group. And then you hit it with a reducing agent, and that turns it into an amine. How many carbons does my alkyl halide need if I'm going to use this method? Somebody, anybody? Somebody give me an alkyl halide I can use this method to create an amine. I'm not going to be able to give you guys review points if nobody interacts.
Did you want a primary alkyl halide?
Got to be a primary alkyl halide.
We can do chlorobutanol.
Not butanol, but just
Mm,
chlorobutane, right? Or bromobutane, chlorobutane works too. But yeah, it has to be primary. That is going to be one of the caveats of this. Well, actually, it's your alkyl halide that has to be primary. It's the only way that this is going to work. And the reason is that this is an SN2 based mechanism. So if you tried it with a secondary or a tertiary, you would get elimination product. And actually the same thing goes for if we want to use the second method, which is the Gabriel synthesis. So this uses that phthalimide ion. Right? You have that, you treat it with base. And then the second step, you can either hit it with acid or hydrazine. I don't know. Seems like the easier thing to remember to me. That would also give you a primary amine. And again, you have to use a primary alkyl halide for this method as well. So these will always create terminal primary amines. Got to be on that end carbon there. Another method, and again, this is because it's SN2 based. So secondary or tertiary, you'll have elimination product. One of the ones we learned about previously would have been if we treated this with sodium cyanide. Again, this would be an SN2 based reaction. So we're going to need a primary alkyl halide. And then we hit it with a reducing agent. Turns out that for the cyanide, we have our common lithium aluminum hydride followed by water. Okay, but what alkyl halide would I need to start out with for this one? Again, it's got to be primary.
It's adding another carbon, correct? For this, so you would start with a chloropropane.
Yeah, so any sort of like a bromopropane, chloropropane, iodopropane. For these, for this chapter in particular, actually, it's a good idea to stick with the bromine or iodine. Bromine's always a safe choice because it's both cheap and one of the more reactive ones. Chlorine's cheap, but not as reactive. Iodine's more reactive, but it's more expensive. So bromine is just a good, safe go-to. There are plenty of reactions where chlorine would work as well, but there are just a few that it doesn't. So like if I'm gonna pick one and go with it, I'll always go with the bromo alkyl halide. Cool, but yeah, the most important thing here is that this fourth carbon is going to come from that cyano group there. So we need to start out with a 3-carbon chain. Okay, if we have a ketone, this would be considered this reductive amination reaction. This is one of the more what am I trying to say? Like flexible of the reactions that we can use. So in this particular case, because it's a primary amine, we would be using ammonia. And then under acidic conditions, we got to hit it with a reducing agent. In this chapter, we learned about this special reducing agent. So I don't remember, borohydride cyanide, something like that. Cyanoborohydride, that sounds correct. But importantly here, what ketone would I need to start out with in order to make this happen?
Would it be a butanone?
Yeah, nice. Yeah, so it has to, you got your 4 carbons, but that ketone group or that oxo group, it's an aldehyde, not a ketone. So I guess I got to be good about that. I hate that they have different categories for those. I wish it was all ketones, but that's a different story. But importantly, the first step here in these reactions is that the nitrogen replaces that oxygen to create an imine with an I, right? So then this further gets reduced to our primary amine, but basically that nitrogen is just going to hop on and take place of that oxygen. So we can't have anything over here, or that would be a primary amine, but it wouldn't be terminal. Okay, so if you have a terminal primary amine, you know that you're going to start with an aldehyde. Okay, cool. And then what carboxylic acid derivative do we know how to convert to an amine?
Is it the SOCl2 with excess?
So we could pretty much start out with any carboxylic acid derivative since we know how to interconvert them so easily. But the last step is going to have to go through an amide. So we know how to convert a carboxylic acid to an amide. We know how to convert an acyl halide to an amide. We know how to convert an ester to an amide. But the bottom line is all 3 of these would have to go through that amide step. And then once we're there, we can just hit it with the lithium aluminum hydride and water and further reduce that to an amine. So yeah, I mean, you could start out with any carboxylic acid derivative. You would just be adding an extra step because the bottom line is you have to get to your amide first, and then that'll be transformed into the amine. Okay. Now, what if instead of being a terminal primary amine, this is still a primary amine, right? Because I have 2 hydrogens on my nitrogen, but it's no longer terminal. Now we only have one method of converting that. So everybody take a second and give me the reagents that you would use for that step.
Dr.
Well,
Chris,
yeah, what's up?
would you like the reactant?
Yeah, both the reactant and the reagents. There's only one way to do this that we know about. Okay, so this would be another example of a reductive amination. So first treat it with ammonia, and then under acidic conditions, hit it with the sodium cyanoborohydride. Importantly though, you know, what I think is probably the harder part of this is what ketone or aldehyde am I going to start with? Right, reductive amination, we start with ketones or aldehydes. What ketone or aldehyde am I going to need? Anybody? Let me get a guess. Sorry, I didn't see the chat. What ketone or aldehyde will we need for this step here?
Is it 2-butone?
Yep, butanone. But unknown. Remember, you got to keep that AN in there to indicate that there are no double bonds, different from like butanone, which would have, you know, a double bond in there somewhere.
Right. Okay.
So this was a common kind of mistake that people make with nomenclature is they remember the ending, they remember the prefix, but then they just kind of slam those two together. Make sure you have that AN, EN, or YN in there to indicate that it's either all single bonds, there are double bonds, or triple bonds. But yes, so 2-butanone. Cool. So actually, real quick before we go on, just get in the habit of being able to determine which ketone. Oh, damn. Well, that gave that one away. Do a few more. These are all going to be the reductive amination. The reagents are going to be the same for all of these. What I really want is for you guys to take a minute and tell me what ketones we're going to need in order to produce these products. Let's do that one. Let's do. Yeah, so take a second and solve these three problems. What ketone or aldehyde would I need to create these? Okay, so what I'm going to do when I do these is, again, sort of noting the mechanism here, how it has to go through that amine. The easiest thing to do is you're just going to erase that nitrogen, draw a second bond, and put an oxygen there. Okay, that's if we can, that's sort of how easy it is to go from the one to the other. In terms of nomenclature, right? So we're going to find our parent chain, 1, 2, 3, 4, 5. This is an aldehyde, so it's going to be a pentanal. And then we have a methyl group at carbon 2, so this is 2-methyl pentanal. Hi, boys. Okay. Again, if I'm going to figure out what my ketone is, I'm just going to copy down what I have. I was kind of trying to throw you a curveball on this one, but yes, this is just an aldehyde that we have here. We actually don't really need to know how to name this one because it's not part of the square is not part of a parent chain. And then lastly, here we have the Cyclo Pentanone. So you see reductive amination is way more flexible than the previous two methods that we learned, the other two methods we learned about in this chapter, the Gabriel synthesis or the sodium azide. Both of those will only create, both of those will only create terminal amines that are primary amines that are terminal rather. So you couldn't create this compound here, or this one here using the other two methods. So yeah, anything you could do with reductive amination, or anything you can do with Gabriel synthesis or sodium azide synthesis, you can also do with reductive amination, but you can do more. So including, I'm just gonna erase this, we'll work from our original problem here. I can even go on from creating this primary amine to now transforming it into a secondary amine. Everybody take a second and tell me what I would need to use in order to get there. That was a terrible question mark. Oh, wait. Way too many bonds. There we go. No, you can't use, so you can't use Grignards with your amines for the same reason that you can't use Grignards with alcohols. And that's because of this proton right here, right? So if we tossed in, let's say CH3, CH2, MgBr with this amine, all that's going to happen is this hydrogen here is going to be replaced and we're going to get CH3, CH3, where our Grignards basically, instead of doing what we want, where what we want is for it to act as a nucleophile, right? That's why we would use a Grignard. But when you ever have a donatable proton, it's going to act as a base. So instead, it's going to be this reductive amination scheme again. You're going to be able to use this same sort of scheme. We just got to figure out what aldehyde or ketone we have to use in order to create our secondary amine here. Yeah, exactly. Not ethanone, ethanal, right? Because it's an aldehyde. Again, I hate the fact that aldehydes and ketones have two different distinctions. They should just be one in my mind, but you know, history. So in this case, I'm going to use first ethanal, which is also called acetaldehyde, and then under acidic conditions, hit it with that reducing agent. And then if we want to just play the nomenclature game real quick, take a second, first find the parent chain. Well, see if you can name it, but if we can't get all the way to the name, see if you can at least tell me where the parent chain is in our secondary amine here. So whenever you're doing your parent chain, you always want to include the functional group. So it's very tempting to say like that this would be your parent chain, okay? That's not the case. And in fact, what's sort of important to be able to see when you're dealing with amines is what to consider the functional group and what to consider the parent chain, or the substituent and the parent chain. In this case, this whole thing right here would be considered the substituent. And this longer chain is going to be the parent chain, okay? And that would be, you know, basically your parent chain isn't going to have the nitrogen in the middle. The nitrogen is always going to be a substituent off of the parent chain. So in this case, we will have 4 carbons. So this is a butanamine located at position 2, right? So that covers our parent chain portion. But now how do I account for these 2 carbons that are on the nitrogen? I don't give them a number. I indicate with what? Yeah. So this would be N-ethyl-2-butanamine. Right. And so again, you sort of, I know it's tempting to sort of want to run your parent chain as if it includes this nitrogen. The nitrogen has to be a substituent off of the parent chain. It's never going to be sitting in the middle. So then if we had something, just to continue on our nomenclature thing here, if we had something like this, I'm missing a bond. What would be the, take a second and see if you can't give me the name there. Actually, let me just do that so it's a little different. Right, so here we have to, yeah, exactly. Nice job. So here we sort of have to decide whether this chunk is going to be our substituent or whether this chunk is going to be our substituent. And we want our parent chain to be whichever one is longer. So this will be the substituent, and these 1, 2, 3, 4, 5 carbons will be the parent chain. There's actually one thing missing from your name, Theo, which would be where that amine group is. Because unlike an amide or a carboxylic acid, we can't assume that it's going to be at the terminal position, just like as with this example here. That dash. So in this case, our parent chain, we have this 1 pentanamine, and then we're going to include that substituent there. So this would be an N-propyl 1-pentanamine. And you'll actually see me doing that approach when I do nomenclature a lot, which is start with the parent and then tack on the substituents onto the beginning. I mean, I'm not saying that that's the only way to do it, but that is how I tend to think about it. And then just to add one more kind of level of complication here, what if, so I have this very similar example here, but now I have a double bond. So first of all, this would be up here. We have something very similar. We have our N-propyl. But now we have two substituents that were, not two substituents, I'm sorry, two suffixes that we have to account for. And so we got to do that in the back half of the name. So this would be pent, I guess it's just one ene, one amine. All right, because I'm going to start numbering from that carbon that contains the nitrogen. Okay. One thing I want to go over that was on the exam that just about everybody got wrong would be the reaction between a carboxylic acid and an amine. So many people said that this would produce an amide, and I get why, because every single other carboxylic acid derivative, the acyl halides, the acid anhydrides, even esters, all you would have to do is combine with an amine and you would get an amide. But with a carboxylic acid, we talked about that this was an exception because there's going to be some side reaction that happens first. And then what would that be? Think all the way back to first semester, like chapter 3 business. Yeah, exactly. So you would have just a simple acid-base reaction here, right? Because before anything complicated can happen with this being a nucleophile and this being an electrophile, this is an acid and our amines are bases. So all you're gonna get is a carboxylate ion and an ammonium salt. And that really messes things up because this is no longer an electrophile and this is no longer a nucleophile. Which is what we would need if we were trying to create an amine. So yeah, so first thing, one of the things that we talked about at the very beginning of this chapter was just how amines play the role of bases and how that's important. For simple amines, primary, secondary, tertiary, the important thing to remember is that tertiary amines are the best bases. Secondary and primary amines, for whatever reason, they kind of switch back and forth. Basically, they're about equal. Sometimes the primary amine is a little bit more basic. Sometimes the secondary amine is a little bit more basic. But the one trend that's always true is that tertiary amines are always the better bases. More complicated, or like in terms of comparing basicity and acidity, or I guess no, just basicity, would be comparing something like this versus this. Which one's the better base and why? Let's take a second and see if you can't tell me which one of these you would expect to be the better base and why. And one thing that might help you do this is to draw the conjugate acid for each one of these.
Would it be the second one?
Is the better base or the worst base?
The better base?
This one is actually a worse base. So let's go over why that would be. So first of all, let me just draw out my conjugate acids real quick. Right, which basically just means I'm going to protonate that nitrogen. Okay, so for this one, it's no better, worse, different than if we were just talking about something like this, diethylamine or dimethylamine, I guess, versus now we draw our conjugate acid. There's nothing really special going on about that ring. It's just kind of there. However, this compound here is very different from this compound here, because this top one, what do we know is special about this top one? Going back to when we were talking about benzene and all that good stuff. Yeah, resonance, but most importantly, not only that it's stabilized by resonance, because we could kind of go either way with that, like maybe our positive charge is stabilized by resonance. What special category does this molecule fall into? Okay, so first of all, we're in a ring. Yes. Is everything sp2 hybridized? Right, so we have now 1, 2, 3 pairs of electrons contributing to resonance within this ring. So that makes this aromatic. And what about the compound below? Is that aromatic?
No,
Why not?
because there's an sp3.
Boom, absolutely. Because now this guy is sp3 hybridized. So this is non-aromatic. Right, so for that nitrogen to act as a base, you would have to break the aromaticity of that compound, which is super duper unfavorable. Okay, another example that's like often thrown into this whole mix is the example of pyridine. And pyridine actually is a good base. It's not like a fantastic base by any means, but it's a decent base. And the reason for that is if I'm going to draw the conjugate acid, both of these are aromatic, right? It all has to do with this pair of electrons here. Up at the top, when we were talking about pyrene, what the heck is that guy called? Something like that. Pyrrole, sorry. We were talking about pyrrole. Pyrrole is aromatic because that pair of electrons is participating in that resonance within that ring. When we're talking about pyridine, this pair of electrons is not participating in resonance, so it can accept that hydrogen. You know, you're not changing your aromaticity. So anyway, it's kind of it doesn't extend too far beyond these two compounds here, but that's the consideration that you want to make when you're talking about these heterocyclic rings and whether or not nitrogen is going to play the role of a base. It will be a good base if the pair of electrons, if lone pair is not in resonance, and it will be a bad base if lone pair is in resonance. Cool. All right, just try to cover some more ground here before we finish up. Another reaction that we learned, or set of reactions that we learned about, was what happens when you react an amine with nitrous acid. So let's first tell me the product of reacting this with nitrous acid and this. And the difference is this is a primary amine, this is a secondary amine. Those will give us two different products. So take us, oh, I'm sorry, that's not what I meant. Primary amine and a secondary amine will each give us two different products. So take a second and see if you can't tell me what those would be.
Is the primary one a diazome salt?
Yeah, so this is going to be, but what I'm going to do is I'm just going to replace the nitrogen. I got the same number of carbons, all that good stuff. But now my nitrogen, instead of being bound to two hydrogens, it's going to be bound to another nitrogen with a triple bond, which means that this one's going to have a plus charge. And so, yeah, there's going to be this counter ion here. When it's a secondary amine, we have this other compound where we now have, it's again another nitrogen that's bound, but this is bound to an oxygen. This is called a nitrosamine. Truth be told, this one here, this nitrosamine, you got to know that it forms because the ACS tells us we do. But really the only other thing to note about this is that it's terrible for you. It's very toxic. Just kind of qualitative information there. This one is arguably the more important reaction because this group here, this diazonium group, is something that's very important, especially when it's attached to a ring. Can anybody tell me anything about the diazonium group when it's attached to a ring?
Oh my gosh.
Are they unstable?
They're unstable if it's not attached to a ring. So if it's not resonance stabilized, it's incredibly reactive. But that's kind of why we like it when it is attached to a ring, is because it's incredibly reactive. And this group plays the role of what? Anybody? Nucleophile, electrophile, leaving group, base, acid. What can I categorize that as?
Isn't it?
Leaving group?
Yeah, so what I want you guys to have glued in your brain is that this group here is synonymous with leaving group. It can be, you can replace it with just about anything. It's really easy to have that act as a leaving group in any number of substitution reactions. So yeah, so just have that glued in your brain. That diazonium group is going to play the role of a leaving group when it's attached to a ring. So anytime you see aniline being hit with nitrous acid, or again, kind of as the book lays out, usually you do sodium and then HCl. But whatever, let's just make it nitrous acid. Anytime you have your aniline being hit with nitrous acid, what that's going to do is convert this into something with a good leaving group. So that next step, whatever the next step is always going to be about substituting out that. So if I have something like this, this is going to be first creating a good leaving group and then substituting that out. Okay, and then the other one that's a little bit different, I kind of have it in a different category in my brain, is if the second step is instead, so there's a list of reagents that you should know what that would do in this second step. So first of all, copper and anything else on the other side, you'll get a substitution reaction that puts that there. Okay, there were a few other reagents we learned about. Here, I'm gonna just do a little wheel here. So, how much space I got? No, it'll be fine. That is a terrible looking benzene ring. I have to redo that. So again, we have this good leaving group. So again, copper and whatever. Another one that we learned about was just water and heat. Take a second and see if you can't give me what that is. Another one was HBF4. And then phosphoric acid. So see if you can't give me those substitution products.
For the water and heat, it adds on an OH group, correct?
Yep.
And for the H3PO4, it adds on a hydrogen.
Yep. So this is a way to sort of kick off that group altogether. Right. Remove whatever, you could have started out with an aniline. If you wanted to chop off that aniline group, this would be a great way to do it. First, turn it into the diazonium salt, then hit it with phosphoric acid. And the HbF4 will just do a replacement with fluorine. Okay. And then there was one other one, which again, I kind of keep in a little bit of a different place in my brain because it's kind of weird. And that is, what happens if I hit this diazonium salt with phenol?
Is it the Azo Coupling?
Yeah, exactly. So this is where you get, this is the only time that diazonium group does not act as a leaving group. It actually sticks around and we have Azo Coupling. To be honest, I am surprised that I'd would have been tempted to leave that off, but out of the course. But I've seen it on the ACS exam before, so it is something that we need to make sure that we know.
Okay. Would you like us to memorize the sigma complex for the Azo coupling?
No, I mean, you don't need to know the mechanism for that one, but I mean, it should, just looking at it, should make sense that all the sigma complex is just like all the other sigma complexes, right? It's basically a carbocation that's resonance stabilized. So while I don't expect you to have it memorized for this particular one, I definitely expect you to be able to show resonance stabilization of charge.
Okay.
Does that make sense?
Yes.
Like, not necessarily for this chapter, I'm not going to be like, give me this, whatever, but totally resonance stabilization of charge is something that we learned about in previous chapters and is something that should be known for the ACS exam. Okay, so that's all the pre-planned stuff that I got. If you guys have any additional questions, hit me.
I had a question for the heterocycles. Why would the C2 substitution give us the most stable intermediate?
Yeah, so that's going to do with sort of the resonance stabilization. So let's look at what would happen. Whoops. I'm assuming you're talking about pyrrole, right? Because that's the one that it's the C2, right?
Yes.
So I guess first, let's summarize here. Pyrrole, when you hit that with bromine, and in the case of pyrrole, you'll do it at low temperatures because pyrrole is really reactive. Always C2. So this will be my product. And in the case of pyridine, oh, that's not correct. Pyridine is actually less reactive, so we're going to have to crank up the heat on that one quite a bit, apparently. That's always C3. Okay. So why for pyrrole is it always C2? Well, it has to do with the sigma complex that's formed. So let's remember in these reactions, what's going to happen is the ring is going to play the role of the nucleophile. So that means this pi bond here is going to reach out and grab that bromine. And if it's in the C2 position, where is the positive charge going to form?
On the C3.
Yeah, exactly, right? So when you add to one carbon, the positive charge is going to go on its next door neighbor. So this is going to be resonance stabilized, so we can draw all these different, let me actually, I'm going to move this down so we can have enough room to draw all these resonance contributors. Now where's the positive charge going to go? My pentagon skills are just no good.
You're okay. It's gonna go on the C5.
Yep, so now my positive charge is moved over there. And then what's the next step going to be in terms of this resonance stabilization? It's actually going to involve this lone pair on this nitrogen. Going to come down. Okay. And I guess actually just to be good, I should draw the fact that this hydrogen is still here in all these structures. The next step is that nitrogen or hydrogen gets kicked off. But this resonance contributor right here is why the C2 position is preferred. What is so special about that resonance contributor?
Leaving room?
No. So it's the most stable, but why is it the most stable? So this is something that's kind of odd because typically we wouldn't think of positive charges being on the more electronegative atom to be good. But there's something very different about, for example, this carbocation and this ammonium ion. The ammonium ion is way more stable. It's not just that it's more highly substituted, it's the fact that carbocations, this carbon only has 6 electrons in its valence, whereas when nitrogen bears that positive charge, it has 8 electrons in its valence. So every single atom in this structure here has a satisfied octet. So that makes it a very stable structure, very stable to bear that positive charge.
Okay, that makes a lot of sense.
And then, just to finish it off here, right? So then the next step would be you kind of got to reverse back around your wheel here, and then this pair of electrons comes down here, and so that will create my substitution product specifically at that C2 position.
Thank you.
Yep.
So back to the nomenclature.
Yeah.
If you name something like methylpropylamine, would that be the IUPAC name or the common name?
Methylpropylamine will be the common name, but amines, a lot like some of the other compound, like it's not the IUPAC name, but really how it goes is IUPAC was established in like the 70s. So if chemicals were widely in use before that time, the common name is, you might see it in the stockroom if you go back, written on bottles. So amines were incredibly in common use even before IUPAC was accepted. So these common names will show up more for certain compounds. Amines are one of them. Right, all those benzene derivatives, they all have those weird names that are established as IUPAC names. That's just because they were already in wide circulation before IUPAC was founded. But yeah, amines are a good example of where a common name, you'll see it a lot. I tend to defer to the IUPAC name because I, grew up in a generation after IUPAC was established. But yeah, we do need to know the common names for some of them just because they are still in common usage. And it's weird, like diethylamine will always be referred to as diethylamine, but maybe like pentylmethylamine won't, because diethylamine is super duper common and the other one isn't. So it also sort of just depends on how widely used that particular chemical is.
Okay, yeah, that makes sense because I was getting confused between the two of them.
Yeah, so if we wanted to do just an example, like diethylamine, again, this would be the common name. If you were going to do the IUPAC name, this would be N-ethyl, F-anamine. You actually don't have to specify the number because there's always there's only two carbons, so it's always going to go on carbon 1. Maybe a better example would be, this would be dipropylamine. This would be N-propyl-1-propanamine as the common, or as the IUPAC. So common IUPAC. Personally, wish we could do away with all common names. It would make my job as a teacher so much easier, but that's the reality of it. Okay, I'm gonna stop this. You guys, I mean,